What's going on, guys? So to complete these energy calculations here, we need to make sure that we have, all right, obviously our gravitational potential energy equation and our kinetic energy equation. If you rearrange the kinetic energy equation, you can solve for the velocity if you know what the kinetic energy is and the mass of the object. Now, for a closed system, the mechanical energy is going to be constant. So if I know that, hey, potential energy here is 6 joules, and the kinetic energy, let's lower this a little bit. Okay. Kinetic energy here is 0 joules at that one point. Then that is telling us that the total mechanical energy at any single point is 6. So if you were to take these guys here, add them up, you get 6. Here, 6, here, 6. So at each of these following pieces of information, we would need to solve, rearranging to solve for height in the equation, which would be the potential energy divided by mass times gravity, and then the velocity, so 2 times ke over m. So let's take a look at the first one. They wanted us to solve for height. So since we already know what the potential energy is, it is 6 joules. And they want h. If I covered up h in the equation, times mass, or divided by mass times gravity. So we're going to crank in 6 divided by the mass of 2 times gravity of 9.8. Let me zoom in here just a little bit more for you guys. So yeah, 6 divided by 2 times 9.8. And we're going to get a height here of 0.306 meters. So h 0.306 meters. All right, B asks you to solve for height and velocity. So you're going to solve for the height the same way. What is going on here? So you're going to solve for it the same exact way and get your final spot for that. Now for the velocity, though, showing out the velocity equation, velocity is going to be 2 times the kinetic energy over the mass and square root that answer. So the velocity is going to equal 2 times your 3 joules over the mass here of 2, and then we're going to square root that. And that's going to kick out an answer of, all right, so 2 times 3, divided by 2, and then we have to square root that answer. And you get 1.73 meters per second. That's the velocity. .73 meters per second. So you're going to wind up going through and doing the same idea, going through that and completing the same tasks. Now for the next assignment, back out just a little bit. There we go. So at each of the letters, they're going to want you to solve for the missing variable. So right off the rip, if you know that the potential energy is 100 joules, kinetic energy is 0. All right, mechanical energy is potential plus kinetic. Now for a closed system, all right, resistance-free cases, so there's no friction or anything like that, no air resistance. The mechanical energy then we're going to say is in a closed system. So the energy is not going to change whatsoever. So it's going to be 100 joules at each of the given pieces of parts. Those are words that I said. Okay. So based upon where the heights are, the positions, and the given pieces of information, you're going to be able to go through and you're going to be able to solve for these missing pieces of information. So A, they want a kinetic energy. Well, that's pretty simple. 100 minus 50 is going to be 50 joules. And B, all right, like the equation we used up top, V is going to be 2ke over m square root. The kinetic energy would be 50 joules. The mass of the object, 2 kilograms. It's just going to be the square root of 50, which is going to come out to be 7.07 meters per second. Now C, well, geez, they don't give us anything. Well, if you look at the ball itself, it's at the same height. So since they're at the same height, the object's the same. So mass times height times gravity, you're going to get another 50 joules here for your potential energy. And again, mechanical energy is constant for this. So since the potential is 50, this is 50. Okay, you kind of go through and figure out what is going on here. And when you're at height of 0, when height is 0, your potential energy is 0. So that's at 2 cases. That would be at case, what are they asking us for? Potential energy would be, all right, so F, since the height is 0, the potential energy there has to be 0 joules. And over here at point I, or position I, you're looking at it, and that would also be 0 joules. So you can go through it like that and help yourselves out to figure those answers. Now on the back side, all right, so how would we go about solving this? There's 2 ways. There's 2 ways. So let's take a look at one of them. Just one of the ways that I was looking at it originally, if you know the velocity, you know that it's going to come to a stop. So you know the initial velocity and the final velocity of 0. And in some cases, we know the distance. So I kind of reverse engineered. So this first one, VF minus VI, right? VF squared equals VI squared plus 2 times the acceleration times the distance. It's one of your kinematic equations. So if you know what this guy is, all right, it's 60 squared plus 2a times 240 miles per hour. Velocity here, v0 is our stopping point. So kind of just reverse this out, subtract it over here, you're going to get negative 0, minus 60 squared, but when you square that negative, it's going to drop out. So we're just going to say it's 60 squared which is 3,600 is going to equal then 2 times A times D, which was the 240. So if you take 3,600, divide it by 2, and then divide by 240, that would have left you with an acceleration or deceleration of like 7.5. Whatever our unit here is, because it's not meters, it's probably like feet per second squared, something along those lines. So with that in consideration, if you're same car, same tires, same road, the acceleration or deceleration would be the same for any of these guys. So you would be able to rearrange it and then solve for D in these missing pieces. All right, so to solve for A, B, and C, you could go about it doing so like that. All right, you would have 40 squared. Right, so 40 squared, what do we got? 1,600 plus 2 times, if we knew the acceleration was the 7.5 times D. So you're going to get 1,600, 40 squared over the other side. Forget about the negative. Divide it by 2, divide it by 7.5. You're looking at a braking distance of 106.6 repeating, 0.67, whatever, however you want to say that. I guess this is feet, we're going to call it. So in the next one, or here's another way you could have done it. Judging by, we're assuming again this is the same car, in the kinetic energy equation, you have 1/2 mv squared. So we're not changing the mass, but we're changing the velocities. All right, so at a velocity of 60 miles per hour, it's going to take us this 204, I'm sorry, 240 feet to come to a stop. So 40 over 60. It's 2/3 of your original speed right there. But we have to square that because in the equation, velocity is squared. And then multiply that and figured, okay, well now we're going slower, so our braking distance should definitely be less. And if we take this new number multiplied by this distance of the original, you come out with the same answer. So you can do that one of two ways. All right, so it's proportionality to the velocity here, or you can use the kinematic equation to solve. So you have a constant mass. They want to figure out what the velocities or speeds are at points B, which is here, C, and D and E. So velocity for these things, you want to make sure that there's no work being added or subtracted here. 35, 15, it's 50, 50, 50, 50. Okay. So total mechanical energy is constant, 50,000 joules no matter what in any of these scenarios. You're solving for the velocity. So velocity would equal 2 times, again, your kinetic energy over the mass square root in order to solve for those pieces, for each one of those. The last one could be done the same way as our guy up top. You could do the VF squared equals VI squared. Equals 2 times AD. Figure out the braking or deceleration for the car, and then figured out that, hey, now it's tripled, All right, how are we going to go about this to figure out what the new distance is? So if you take these two in consideration, you have d, you have initial velocity 50, this would be 0. You can solve for a and then use that equation again, except you would have a here and 150. You would be able to figure out the exact distance, or like the other one we did up top, the car speed. All right, so like the work done by the brakes changes the car's kinetic energy from its initial value to 0. This work is equal to the force of friction causing the skid marks multiplied by the length of the skid marks, since work is equal to force times distance. So when the car speed is increased from 50 kilometers an hour to 150 kilometers an hour, proportionality or proportional. All right, if you're changing v into this equation, if you triple the velocity, 3 squared would be 9. So 9 times kinetic energy was increased. So by increasing v3, it means the kinetic energy is increased by 9. The force of friction between the road and the tires skidding does not change. So the distance or length over which the force is applied must increase by 9 times as well. So you would have your 9 times what was it, 15 meters, and cranks out to be 135 meters long. Okay, so that would be your assignment there.